0. It could have a 0 history, well, when the Turing machine is looping, for example. That would, yeah. And at most 1, because if it's deterministic, right, then each configuration is determined by the previous one. And so, once for a given M and W, once you start here, the rest are determined. So you will only have at most 1 history. Okay? Now, how about non-deterministic machines? Well, they could, they might have many computation histories. With just a given single input W, each there'd be like 1 history that would correspond to 1 branch. So if you look at the history, the configuration to configuration in a non-deterministic machine, that just non-determinism in this sense for a Turing machine just means there's at a given point in the computation you might have more than you'll have more than 1 possible configuration, next configuration, right? So if you go down a branch and it ends in a leaf, that's an accept or a reject state, then all those branches that start from the root node, the start configuration, if you like, and you go down all these various branches, and the leaf of each branch is a reject or an accept state, then you will have, for each branch like that, for each path, let's say, from the root node to the accepting or rejecting leaf node, you would have a history for each path, and you may have multiple paths, accepting or rejecting paths, if you like, in your tree. So, but that's non-determinism is more complicated. So from now on, we won't. We'll focus on deterministic machines. Okay. All right. Now, the previous board I mentioned just briefly that one of the reasons one of the motivations, if you like, of talking about this computation, here is shortened computation history, is it allows us, it helps us in undecidability proofs, and now we'll start getting a taste. So we will show we'll give an undecidability proof that actually uses the method of a computation history. It'll use the computation history of a particular machine, Turing machine, and we'll use that to create the undecidability proof. Okay, so that's what we're going to start doing now. Now, the machine I mentioned a bit before, it's not your ordinary Turing machine. It's a variant of a Turing machine, more constrained than usual. Well, I'll give you the name first, and then describe what it is. So it's an LBA, and you'll hear that abbreviation a lot. And it's an abbreviation of a linear bounded automaton. Now, the word bounded, bound in the sense of constrained, and so I'll explain now what an LBA actually is. So imagine this felt tip pen here. That represents the length of your starting, well, your W in effect, your input string. Okay, and imagine the tape, the Turing machine tape. Now we'll use Sipser, so we'll start here. Here's like the left edge, and the tape just goes on infinitely to the right, your right, that way. Okay. Now the input tape that we've been calling W up to now, it will be a finite length. Let's say it contains little n symbols. Okay, so the size, the mod of W is little n. All right. Now, an LBA, so this variant of a Turing machine, it behaves in the following way. Its header is not allowed to move outside the boundary of the size of this tape. So if the number, like if your initial W, your initial string that goes into your Turing machine, if it's of length little n, okay, so your header is not allowed to go to the left or to the right of this string, where the length of this string is n. Now it can move back and forth within that, within the, where my two fingers, they're the boundaries. Okay, so the LBA, linear bounded automaton, is just like an ordinary Turing machine, except that the header, if you like, the read-write head, is not allowed to go to the left of this first square, and it's not allowed to go to the right of this last, the right square. Okay? Now it can move back and forth within those two boundary points, but it's not allowed to go outside. Okay? That's what a linear bounded automaton is. Now, if the Turing machine, this LBA, if it attempts to go to the left of this boundary, it just stays put. Okay, may change all the other things, but its position won't change. It'll just stay at the leftmost square. And similarly, if it attempts to go to the right of the rightmost square, it can't. It'll just stay at that square. You know, it may change the other things, change the state and whatnot, and what gets written. You know, all that can change. So it's still a Turing machine, but it cannot move outside these two boundaries, where the length of this string or is n. So you can overwrite the characters and whatever, but it's constrained, right? It's bounded, and that's what an LBA is. Okay, hope that's fairly clear, right? Well, that's what I've been saying here. Okay, and you know, if it tries to move, if the head tries to move either end of the input, it just stays where it is. Now, we had something similar, a bit of discussion on my part earlier, or quite a few lectures back. Similar to the way that the read-write head's not allowed to move off the left-hand end of the tape. Remember that, you may remember the discussion. You know, why have a left-hand end at all? Why not just have an infinite tape both ways? But anyway, okay. So it's a similar phenomenon. If you try to move the head to the left of your first square, you can't. It just stays there. So the head position remains at that first square position. Okay, so it's similar, but now it's not only at the leftmost square; it's also at the rightmost square. Okay, so it can move in between, but it can't transcend. It can't go beyond those two left and right boundary points, boundary squares. Okay, all right. Well, next session.